All right, good morning, everyone. We can see our due dates of everything coming up. No surprises for 5.4 and 6.1, my math lab homeworks. 6.2 we should finish today, so we'll make that due in a week. The next Excel file that we're going to do is 6.1 fund. I'm going to have that due on the 3rd. I'm giving you a couple extra days on that one because your project is due right around that period as well. In fact, I think I said the project was due on the 2nd? Either the 1st or the 2nd. Someone wants to type in chat which one that was. Actually, I want to confirm that myself. December 1st. Here we go. The 1st, but we should make it the 2nd right now. So I want to stick to that original due date. And I know that to some of you that might have seemed strict because you're doing your budget for all of November. And like, oh, well, how am I supposed to get it done if I have to finish everything on that last day? Well, I had said that you would be able to work on that project the entire time because you can just build up. So this is the due date of everything coming up. And yes, I do have your 4th video quiz due on the same day as the project. But as you've seen, these quizzes are nothing too crazy. They're 4 or 5 questions, usually pretty intuitive as long as you watch the videos that I tell you to watch with them. Yeah, so there we go. There are all our assignments coming up. If you have any questions, per usual, you can ask or email later. Our final exam is not too far around the corner either. That's going to be probably the 10th and 11th, but I'm not putting that down yet because I'm still making sure that's the dates I want to pull for it. All right, so we are going to pick up where we left off, and that is in just kind of doing one more thing in 6.1. And then we'll get into 6.2. Where are we? Boom, here we go. And it's about, here we go. We had our compound interest formula, compounding annually. We said that this formula right here, and at this point I will tell you, it is on your formula sheet. I feel like I've very strongly alluded to the fact that it's on your formula sheet. However, I feel like it's so important that you should have that memorized, and it's not an extremely complicated concept. It just says that the newest amount equals the oldest amount times the growth factor or decay factor, if it was a minus, and then your exponent is just how many years have gone on. But we said that was only for compounding annually. So then I'm just gonna leave some of this stuff spoiled up here, but I'll show you as we're talking about it. What if we were to compound on a shorter timeline like months or quarters or days? What change, and I have it in quotes, but I don't necessarily need to, but it's just kind of a math thing that I have in quotes. What change does the R go through in this formula? What change does the T go through? And this is something where if we had lots of time in class, we would actually, spend 15 minutes kind of, getting our heads together and talking through this, but we're going to just kind of push it a little more on you. And that hint I would give my students is remember periodic rates. Also remember the idea of total number of payments. So periodic rate is when you took your annual rate and you divided it by the number of periods in that year. So if you were talking about monthly, you would take the annual rate and divide it by the number of months. If we were talking about daily, we would take the annual rate and divide it by the number of days. This is what gives you just a little slice of the rate and the proportionally correct slice of the rate. So if you were going to pay 12% over a year, if you slice that interest into monthly accrements or monthly compounding, that means that 12% that you would have effectively felt over a year, when you only look at one slice of it, is now 1%, because 12% divided by 12 months is 1. Or if you were to look at this as quarters, that 12% divided by 4 would be 3%. So you'd be paying 3% for January, February, March, then 3% for April, May, June, et cetera, et cetera. but you still have that compounding effect, which means that you won't actually pay exactly 12% over a year. You're going to be paying a little more because that interest is going to compound. So what I was just talking about, how we took the annual rate and divided it by the number of months or number of quarters, whatever, the R in the formula turns into an R over N. That's all you do, is you just take the R and turn it into an R over N. So instead of using an annual rate, you're using a periodic rate. That's the change that you can see. That's not good. All right, sometimes this happens. I'm probably gonna have to close this and open it again, if that actually fixes it. Dun-dun-dun-dun. Thank you for your patience. Chapter 6 notes to share. Nope, that's 8. I can read. Chapter 6 notes to share. Where did they go? I hope I didn't accidentally save that. There it is. Please. All right, there we go. Got it. So this R turns into R over N, so that we go from an annual rate to a periodic rate. That's what I was just talking about. It's the periodic rate instead of the annual rate, which is why the R turns into R over N. Now the other thing is, we say, what about the time? This was supposed to be the number of times that you compound, which if you're compounding every year, it's the number of years. But if you compound every month, 1 year means that 12 compounding intervals have passed by, which means the exponent would be a 12. 1 year, if you compound monthly, the exponent's a 12 because there's 12 months in 1 year. So that's why I said, think about the number of payments. So if you have a loan that you borrow for 1 year and you pay it monthly and you pay the whole thing off in 1 year, that means you would make 12 payments. 12, which is the number of months per year, times the number of years you pay, 1. Or if you have a 2-year loan, you'd be making 24 payments, 12 times 2. If you have a 5-year loan, you'd be making 60 payments, 12 times 5. So the exponent goes from just being the time in years to being in t, which n is the number of periods per year, t being the number of years. So again, the exponent is really the number of times you compound. If you compound annually, that means the exponent is the number of years. Compounding any less means you have to take the number of years times the number of compound intervals per year. Now, when you're putting these in your calculator, I have this bolded and capitalized, and now I'm red underlining it. Always pre-multiply the n and t in your exponents. You absolutely have to pre-multiply your n and your t in your exponents. That is extremely important. Now I say always, and I could put a little asterisk here because there are some calculators where you don't have to do that. Most of us don't own those calculators. I don't own that calculator. Some students come in with like a banging TI 92 or something like that, and then that one can handle it or something in that ballpark. I don't have one, so I don't remember exactly. But the point is, fancy calculators, you might not have to do this, but I assume you don't own a fancy calculator. So by pre-multiply, I mean, just take that n times t. So if you had a 5-year loan and you were paying it off monthly, or you put a sum of money into a savings account for 5 years and you were accruing interest monthly, you would take that 5 times 12 and have a 60, and that's what you would type in your calculator in this formula. And before I go on to my next example, just showing the difference of using this formula versus the previous one, in Excel, we can see each and every iteration of interest and future value calculations. The formula is just better when we want one specific value in time. This right here, I've already talked about dozens and dozens of times. It's nothing new. So that's why I just kind of like to have reminders here and there, but I don't need to talk about that for 5 hours. All right, so example number, whatever, doesn't matter. Bob, our buddy Bob, deposits $10,000 at 2% interest, compounding monthly. How much money Bob have after 1 year, 10 years, 40 years? How does this compare to when he compounded annually? Now, this is a callback, the last question. This right here is a callback to an example I no longer have typed up here, but you should have been taking good notes. Hopefully you have those answers written down. I will write the answers down from previous, so we don't have to go and recalculate them. But this is just going to introduce the idea of diminishing returns, which sounds like a bad thing, but is still actually a good thing. I mean, it's just that we'll get into it. All right, so Bob deposits 10 grand, the same amount that Bob put in our original example, at 2% interest, same as before, but now we compound monthly. This is the only thing that's changing from before when Bob put in $10,000 at 2% interest compounding annually. And we looked at how much he had, like 1 year, 5 year, 10 years, and 40 years, and I'm just skipping the 5 in this instance, which is not a big deal. As a reminder, because we're compounding monthly, we have to use this new formula, which is A equals P times 1 plus R over N raised to the N times T. That's the new formula I gave you, which I'm not even going to hint that you have to memorize. It's on a formula sheet, which, by the way, no, not that. All my things got reorganized. This is your formula sheet. So I'm going to make this available in the next class or two. So you should see it by the time you come back from Thanksgiving break. And these are the finance formulas you'll have for your final exam. You can see that the one I said you should memorize is up there, but still please memorize it because it's a great concept. The one we just gave you is up there, as well as, oh boy, 1, 2, 3, 4, 5, 6 others as well. And we're going to get into all of these over the next couple of weeks, mostly in chapter 9 for the later ones, but we'll see them slowly build up. And you can see a lot of the same familiar pieces, this 1 plus R over N raised to the NT, 1 plus R over N raised to the N, 1 plus RT, 1 plus R over N raised to the NT, 1 plus R over N raised to the NT, 1 plus R over N raised to the negative, but still an NT. So it's kind of cookie cutter, but there's a lot of rearrangements, and that's why I'm not going to make you memorize these formulas in a quantitative reasoning course. There's no reason to memorize these. People in finance half the time don't memorize these. They just use an Excel spreadsheet or something like that. All right, but let's focus on that another day. Back to our example. So let's identify the important bits. $10,000, that's our principal, that's our starting amount. It is extremely important that you understand how to distinguish a starting amount versus an ending amount, because these problems are not always, this is what we put in, and then they ask how much do we have later. Sometimes they'll say, we know how much we have now, how much did we have in the beginning? And there are formulas on that sheet that you use for that. But you have to know whether you're identifying the P, which is the starting value, or the A, which is the ending value. All right, the 2%, that is clearly the R, but we'll go ahead and write that as a decimal since I'm not going to use Excel, and it's 0.02. Compounding monthly, that means the N, the number of times we compound per year, is 12. Quarterly would be 4, semi-annually would be 2, daily would be 365. All right, and then these are our T's. T's, I'm not saying T times S, I'm just saying it's a T, and a T. There's 3 of them, so plural. Those are the 4 numbers we put into this formula, and that's it. So for 1 year, I really hope I don't actually hit save at all. That would be A equals 10,000 times 1 plus 0.02, that's the R, over N, which is the 12, raised to the NT, which is 12 times 1. Now, before you put this in your calculator, I said to pre-multiply the exponents, which 12 times 1 is 12. So that's 10,000, parentheses, 1 plus 0.02 over 12, raised to the 12. See, we're going to gain money 12 times. The exponent turns into how many times we gain money, or have to pay money if it's a loan instead. Ignore that stuff. So 10,000. Your calculator, you may have to hit times before the parentheses, so be careful. 1 plus 0.02 divided by 12. Close the parentheses. And the exponent is this little, what we call a caret button. And then raise it to the 12th power. I am telling you, you have got to practice this. Don't think that you watching me do this is going to be good practice for yourself. It's not. I'm just giving you confirmation on how this thing is done. I hope that you're plugging these in your calculator as well so that you can see how to get the right answer. Because when you're doing your homework, I guarantee you're going to make a mistake somewhere. You're going to miss a parentheses. You're going to miss a division. You're going to forget to pre-multiply the exponents. And you might get answers that don't make sense. So 10, 201, 84. Let me do this so I can see the calculator at the same time. All right, so there's how much we have at the end of year one. This is our end balance. How about 10 years in? A is now 10,000 times, see, we don't take the previous ending amount. We don't have to go from 1 year to 2 year to 3 year to 4 year. This goes straight to the end. If we wanted to find all the intervals in between, we would have to do it month by month. We would have to say month 2 amount is the month 1 amount times the growth factor, which is really this. This is now your growth factor because your annual rate has become a periodic rate. All right, look at how much of this formula doesn't change. The principal doesn't change, the rate doesn't change, the end doesn't change. The only thing that changes, I'll do it in a red color just to show you the only thing that's changed, is this. The years went from 1 to 10. So that's 10,000, parentheses, 1 plus 0.02 over 12, raised to the 12 times 10 is 120. So I can even just do this. I can hit second enter to recall that function and just change the exponent to 120. Look at how quickly I did that. I could have typed the whole thing again. You get 12,211.99. That's an ugly looking 9, isn't it? There we go. A little better, a little prettier. Now let's do it for the 40 years in. Our future value is 10,000 times 1 plus 0.02 over 12 raised to the 12 times, and again, the only change in this formula is the time, which we're now 40 years in. 12 times 4 is 48, so that'll be 480. So it'll be a $sign. I can hit second enter, and I can just use my arrows to move around and change the 120 to a 480. Or I could manually retype everything. 10,000 times parentheses 1 plus 0.02. Excuse me, I know I'm coughing a lot today. Divided by 12, close it, raise it to the 480. See, there I just typed everything out again. Same answer. Which is $22,240.59. Now, let me show you if I'd done this wrong. If I hadn't pre-multiplied the exponent, if I had left that as 12 times 40. So 10,000 times 1 plus 0.02 divided by 12. Close the parentheses. Hit my exponent, and now I'm not going to do 480. I'm going to do 12 times 40. And I'll explain what happens. So, oh, okay, well, that's exactly what you have here, so that should be right. That is definitely wrong. We definitely do not have $400,000 after 40 years at a 2% interest rate. I hope that seeing some of the examples over the last week kind of cement that in, that in order to hit hundreds of thousands of dollars on a fairly small deposit, we have to have a significantly larger rate, like 7, 8, 9% probably. So this answer does not make sense. The reason is the calculator thinks that this is the exponent, then this times 40 is like having a times 40 out here instead of it being in the exponent. And man, oh man, does that thing just take the answer and shoot it off to the moon in a completely incorrect way. So be careful with that. That's why I said always pre-multiply your exponents so that you don't make that mistake. Now again, some of your calculators, when you hit your exponent button, it may actually make it look like an exponent. So it takes it, it writes it up here instead of in the same kind of horizontal plane. In that case, you could have the 12 times 40 there, but it's just a good habit either way. All right, so the second part of this question was, how does this compare to when he compounded annually? So when we compounded annually, just to refresh us, so this was the example we did, I believe we did it either 1 or 2 classes ago. The 1-year number was 10,200. The 10-year number was 12,000. 189.94. And the 40-year number was 22,080 and 40 cents. I just wanted to not have that go off the margin. $22,000. Oops, put my comma in the wrong spot there, didn't I? 80, 40. There we go. So how does this compare to when he compounded annually? What I mean is compare this number to this number. What do you see? I mean, by compare, I mean just make a very simple analysis. Which one's bigger? Well, this one's bigger. When we compounded monthly, we got more money. So we earned more money by compounding monthly for 1 year. Let's see if that continues on. So look at this. Comparing the 1 year to the 1 year number, we made an extra $1.84. Okay, are we ringing any bells over that? No, we made an extra $1.84. But are we sad that we made more money? No, we made an extra $2. All right, we can go buy a half a Chick-fil-A sandwich with that. Cool, whatever. Now let's compare the 10-year number, 12,211.99 versus 12,189.94. Okay, we're picking up steam a little. The compounding monthly again is larger, and now let's see, 189 versus 211. That's about $20. It's about $22 more. So 1 year in, we had about $2 more. 10 years in, we got about $22 more. All right, so that was true for the 10-year as well. You think it'll be true for 40 years? Well, let's compare the 40-year number to the 40-year number. 22,240 versus 22,80. So again, the compounding monthly is a bigger number. You're not going to become a millionaire over this, but now we have roughly an extra $160. So 1 year in, we had an extra $2. 10 years in, we had an extra $22. Now we got an extra $160. Now that $160, again, it's not going to make you a millionaire, but I mean, that's a couple fancy dinners, or that's your electric bill, not in December in Hampton Roads maybe, but that's an electric bill at least 1 month out of a year. So the point is, by compounding more, you make more. By compounding more frequently, make more money. By compounding more frequently, you make more money. So what about if we went from monthly to daily? Do you think that we would make a significant amount of money by doing this daily? Well, let's just look at the 40-year number. So 40 years in, this formula would become A equals 10,000, parentheses, 1 plus 0.02 over. Now the n is the number of times we compound. We're going to daily. There's 365. I was saying 3 when I was supposed to be writing 5. That threw me off. There's 365 days in a year. So the exponent would be nt 365 times 40, which even me, I'm going to have to do this just to save some time. So our exponent is 14,600. So if we do 10,000 times 1 plus 0.02 divided by 365. Then raise the exponent to the 14,600. We get $22,254.92. So 254. Now let's compare the compounding monthly to the compounding daily. That's a 4254. You can see it here. So when we went from compounding annually to monthly, we gained an extra $160. So you think, okay, but going from compounding once to 12 times, that's 11 more times per year, we made an extra $160. So what some people might think, and I understand why they would think this, is that if you compound daily, you're going from 12 to 365. So that's like 350 more times a year. Like, not exactly like, I'm just rounding. So, oh man, compounding 11 more times a year made me an extra $160. So compounding an extra 350 times, that ought to make me a millionaire, right? Actually, you make that margin of increase is smaller. You go from 240 to 254, you've only gained an extra $14 by compounding your interest 15,000 times instead of 500 times over that interval. And this is because this 2%, when you pay that out daily, you're making a sliver of a fraction of a percentage. So you're making microtransactions on a daily basis. But at least those daily basis microtransactions do get you a little more money. But it's less money. Going from once a year to 12 times a year, we made that extra $160. Going from 12 times to 365, we made an extra $14. This is known as diminishing returns. Diminishing returns means you make more, the increase is becoming shallower, becoming smaller each time. So the increase is becoming smaller. I'm not saying that your money becomes smaller. I'm saying how much it goes up is shrinking. So we went up $160, then we went up $14. That's what I mean. We still made more money, but the increase has decreased. It sounds weird. I like to call this the Dorito problem. You open a fresh bag of Doritos and you're hungry, so that first chip, best chip of your life. And then you have your 12th chip and it's still really, really freaking good. It's not the best chip, but it's really awesome. And then you have your 20th chip and it's still really good, but it wasn't as good as the 10th chip. And then you have your 50th chip and you're still eating, so it's still a positive mindset there somewhere. That's your increase. But you're not as happy eating that 50th chip as that first chip or even that 10th chip or 30th chip. By the time you eat that 100th chip, I mean, again, you're still eating it. You must be getting something good out of this, but your belly's starting to bloat. You're starting to regret the next one and the next one and the next one. So like, do I really need any more at this point? And again, I'm not saying that it's bad. And yes, you know, eating a whole bag of Doritos would be bad. So the analogy falls apart a little bit there, but again, you get the idea. It's your enjoyment. You still have an enjoyment, but it's marginally reducing with each chip. That's diminishing returns. Diminishing returns is not a bad thing financially because you're making more money. It's just that the more money gets smaller and smaller, and that's all based on how frequently you compound. So going from annually to monthly is a pretty solid increase, but going to anything after that is going to drop off. If you compounded every second or every tenth of a second or every snap of a finger, that increase again will be, you'll gain more, but it's marginal. All right, so now what I want to do is, I'm actually going to pull back that formula sheet. And I'm going to do this. I'm just going to copy paste because I don't know why it's not on this. There we go. One more formula in 6.1 before we move on. Present value needed for a goal, compounding n times. So this works for compounding annually or compounding monthly or daily. If you wanted to compound annually, you just make the n 1. And check this out, if the n is 1, you don't really need to write that letter because r divided by 1 is r. And if your n is 1, you don't really need to write 1 times t because 1 times t is t. So you can actually argue that's a second version of the formula. Whenever you have a formula with an n, if you want to know what it is for compounding annually, just get rid of the n's and boom, there's your formula. It would be p equals a over 1 plus r raised to the t. Take a look at that formula versus this formula. If you took this section right here, and instead of multiplying it by the p, you divided it by the a, that's exactly what this formula is. If you, instead of taking this and having it being multiplied by the p, you divide it by the a. That's actually just solving an equation. It's like solving 10 equals 2x. You divide both sides by 2 to solve for x. It's literally the same thing. It's just instead of dividing by 2, we divided both sides by this parentheses, so it makes it seem weirder. All right, but of course in the actual formula, we don't leave the n's blanked out. I was just pointing out what you could say it is for compounding annually, so that you don't have to write over 1 and 1 times the exponent. So it's kind of like there's a freebie formula in there. So this is what you do. You use this formula when what is known is the ending amount instead of the starting amount. You use these formulas when the known is the starting amount, because P is the starting amount. When you know the starting amount, you use this formula. When you know the ending amount, you use this formula because A is the ending amount. You want the letter that's by itself, you want the letter by itself to be the thing you don't know. That's what's important, and this is the #1 mistake that students make with these, is they don't take the 5 or 10 extra seconds to determine whether the $10,000 I give you is the starting amount or the ending amount. Half the time, they just assume it's the starting amount. Context is key. So the problem will make it very obvious if you pay attention whether the 10,000 or 53,000 number they give you is the starting or ending amount. So let's try out an example. I don't know why my font is so ridiculously big. Bob has, I can't read this number I've written down. 1 second. It's 37,000. $6.11 after having deposited some money into a 4% compounding annually account for 10 years. How much did he start with? How much did he start with? How much did he start with? That is not the ending amount, that's the beginning amount. That is what's unknown. The starting amount is the P in the formulas we've given you so far. That's the unknown. So how am I going to use a formula like this or this, I'm sorry, this or this, if I don't know this number? What do I plug into my calculator? You can't use it. You can't use this formula this time. You can't use this formula this time because we don't have all the numbers that go into that side. So that's why we definitely know we need to use this formula. Let me just get all this on the same screen. There we go. So the 37,000 number, that is not the principal, that is the ending amount. That is this number. And you don't want to be plugging a number in an equation in one of these formulas on the side by itself. That's a horrible idea. The 4%, that says your R is 0.04. The 10 years, that's our T. We're compounding annually. So since this formula, I did not give you a version that doesn't have the end, although I technically did. I said just ignore these. So since we're compounding annually, if you prefer writing this formula that way to have a secondary version of it, that's the formula you'd be plugging it into. Or if you want to use the one I give you directly, compounding annually means n is 1, not 12. That's another mistake people make. They'll say compounding annually is 12. No. Yes, there's 12 months in a year, but they're not saying we compound monthly. They said compounding once per year. If I say compound monthly, that's 12 per year. Big distinction. So plugging these into the formula, say P says P equals 37, $6.11 over, parentheses, 1 plus the r, which was 0.04, divided by the n, which I'll write is 1, raised to the nt, which is 1 times 10. So that's $37,006.11 over 1 plus, I don't really need to write the divided by 1, even though it's still okay to be there. But I said you definitely need to pre-multiply the exponents to make that a 10. Now again, just for an alternate version, so that's a 6. If you don't write the divided by 1 because you know you don't need to write divided by 1, that's what you get. Oops. So $37,006.11 divided by parentheses 1 plus 0.04. I'll type it in both ways, so I'll do this middle one first. So divided by 1, close it, raise it to the 10th power, hit enter. And we can see that I goofed up. I missed a 0, so let me hit second enter. I can actually go to where that is, hit second insert, and just fill that 0 in. There we go, that's what I expected. Putting $2,500 away for 10 years was not going to turn into $37,000 at 4%. I knew that was a mistake. I looked at what I typed and I saw my missing 0 because this calculator lags. If I was doing this in person, I would have never made that mistake. If you type it in the right way with a little asterisk, by right I don't mean correct, I mean the far right side, 37,006.11 divided by parentheses 1 plus 0.04, close it, raise it to the 10th, you'll get the same answer. Now if we compounded monthly, we definitely would have needed the fraction and then the divided by 12. The exponent would have been 10 times 12, which is 120. But you can see rounded to the nearest penny, we started with 25,000. Ooh, that was wackadoo. How that happened, but that's all right. There we go. I might not be able to say I might have to say that 6.2 homework due date's going to change. I forget how much material is in 6.1 every year I teach this class, every semester I teach this class. So this is a big difference. Now, how could you know that you did this wrong? What if you used the wrong formula? What if you used the wrong formula? What if you did this? What if you used the A equals 37,006.11 times 1 plus 0.04 raised to the 10? If you had typed that in the calculator, there's a way that you can instantly tell it's wrong. $37,006.11. And you know how you instantly tell that it's wrong? You ask yourself, you know what it's going to be. Does it make sense? All right, so I'm using the wrong formula. When I hit enter, I can instantly tell I've used the wrong formula if I pay attention and ask, does it make sense? I got $54,778. I'm not even going to... Word is being weird today. $54,778. I will put the pennies, 8 cents. Does that make sense? Bob ends with 37,000 and he had started with 54,000? What? You hear how high my voice is going? All the inflection here? That is completely trash. That cannot be. How would you invest in an account earning you 4% per year? How would you ever start with 54 grand, 55 grand, and end with 37,000? Get your answers and put them in context, because if you just get an answer and slap it in my math lab, you're going to make lots of mistakes. This is the point of this class. One of the many points of this class. It's always analyzing your answer, checking your work, essentially. All right. And I'm looking for something. All right. Last formula of the section. I was just making sure that it was in this section because they a year ago they reorganized what formulas in what sections. Some of these used to be in like chapter 9. Find the annual percent yield, something we haven't talked about since the first couple weeks of class, given an annual percent rate. This formula, I'm going to go back to the formula sheet just to copy paste it so I don't have to take an hour for that. It's right here. To find the annual percent yield, which we've called APY, annual percent yield APY, this is what we call an effective rate. Due to compounding. Compounding. It's the effective rate due to compounding. So earlier, I'll be scrolling back in a second. We said, all right, when we compounded annually after the first year, we made, where is it, 10,200. But when we compounded 1 month instead, when we gained money more frequently, even at the same annual rate, we gain a little more money, which essentially means we could have made a whole new problem where we only gained money once, end up with the $10,201.84, and figure out what that rate would be. And that's what we call the effective rate. So it's kind of like ignoring the compounding intervals, just knowing the ending amount, and then finding the rate based off of that. That's what we're talking about here. It's saying that this number right here, if instead of compounding 1 time per month, if you just compounded only once, what would the rate need to be to make that extra $1.84? Now, since that's not a very big increase, obviously your effective rate is somewhere in the 2% margin, but it's going to be just a little higher, like 2.1 or 2.05. And the bigger the rate, the bigger the gap. If you had like a 10% rate, then the effective rate might be like 10.9 or 11.2 maybe. If you have a 22% rate, the effective rate might be like 25%. But again, let's get back to where we actually were. That's what we're talking about. Again, ignoring the middleman of compounding intervals, what rate would you need to match that if you were to only compound once? You know, when you go look at credit cards or home loans, they give you 2 different numbers. They'll give you an APR and an APY. And if you get a mortgage right now, they might say, all right, well, the mortgage is a 3%, but that's if it was, you know, just compounding annually, but in reality, we're going to compound it monthly. So the effective rate is like 3.1%. Same with credit cards. You might say, oh, this credit card's got 22% interest annually, but that makes the effective rate like 23%. And I'm just, you know, guessing some numbers here off the top of my head. Look at how similar this formula is. It's got that 1 plus r over n. It's got an exponent that's an n, but there's no t here. There's no t here. And you know why there's no t? Because we're looking at this as an annual basis. T, that doesn't say not, that says no t. The t here is always 1. Because we're looking at it a year-by-year basis. We're looking at, instead of compounding 12 times in 1 year, what would the effective rate be if we only compounded once that year? So we don't look at this for multiple years, just 1 year. So that makes this really the exact same thing as this bit of the formula. It's 1 plus r over n raised to the n times 1. There's this extra -1 here, and there's no p in front of the parentheses, so that might throw you off. Do you have to memorize this? No. Do you have to know how to use this? You bet you do. So it's just there's nothing that goes in the front of the parentheses, and then there's a -1. So let me explain what the -1 does. We're never going to derive these, but I like to at least partially explain them. You're going to be getting a decimal value out of this. As a decimal, 1 is 100%. So when you do this 1 plus r over n raised to the n, you're gonna go from having 100% that you started with to something like 107%. That's what you're ending with. You gain that extra 7%. But the effective rate, you can't account for the original 100% you have, so you subtract off the 100% you started with. That's what that does. It gives us the difference of how much we end with and how much we start with. So this is the percentage we end with, this is the percentage we start with. Subtracting them gives us the gain. That's what the 1 is in terms of concept. All right, still not in 6.2. Example. Bob deposits money, not telling you how much, into an account that accrues interest monthly at 12% APR. What is his effective annual rate, aka the APY? EAR, APY, same thing. Some people might go EAY for effective annual yield. Some might say effective annual rate. Some say annual percent yield. They are all the same thing. All we got to do is use this formula. We don't need to know how much money Bob deposits. That's the cool thing. The amount you deposit does not affect the yield. That's why when you look at a credit card, they can give you both those numbers. It doesn't matter how much money you put on it. That's when you get a mortgage, they give you those two numbers. It doesn't how much money you borrow. The yield has nothing to do with the deposit amount. It just has to do with two things, your annual rate and the number of times you compound. So our APY, I should be doing this in blue. Doesn't technically matter, but well, the R would be 0.12, and we're accruing interest monthly, which says the N is not 1, it's 12. That's the two numbers we're slapping in here. So our APY is going to be parentheses 1 plus 0.12 divided by 12. They don't have to be so symmetric. I just did that because this relates to an example we did at the very beginning of the semester where we were calculating APY in a different way. We actually took the ending balance, subtracted the starting balance, and then divided them. I'm sorry, I said subtracted. Why did I do that? We took the ending balance and divided it by the starting balance, and then we converted it to a percent. And then raised to the n, which is 12, then a minus 1. I don't have to adjust anything here. I don't have to pre-multiply an exponent because there's no multiplying in the exponents. We just go parentheses, 1 plus 0.12 divided by 12. Close the parentheses, make an exponent to a 12. Now, if you have a calculator where your exponent, it's smaller and above, you might have to hit the right arrow to get out of that, just fair warning. I don't, though, because it doesn't make it a fancy thing. This is not a fancy calculator. So then minus 1, and we get 0.126825, blah, 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 blah. That's not a percent. We got to convert it. We got to multiply that by 100, move the decimal right twice, whatever. So it's 12.6825%. Let's say I round to 1 decimal place. So that would make it 12.7%. Actually, I take that back. Let's go 2. I know I usually do 1, but let's just mix it up, which would make it 12.68. And if you go back to that TV loan problem that we did together in class, we calculated an effective rate or an annual percent yield of 12.68. See, if you only gained interest once over the year, you would gain exactly 12%. But because we gain money 12 times instead of once, that means effectively we're earning 12.68% over a year. So if Bob deposits $100 in, instead of just getting $12 for free, he's going to get $12.68 for free. Now, depositing $10, obviously that wasn't a big change, but let's say Bob deposits $100,000. That extra 0.68% can get you a few extra bucks. That's a little more significant. All right, so 12%, there's not a lot of loans you're going to be getting at 12%. That's not a lot of credit cards that you're going to get at 12%. Let's do a credit card number more like 21%. So credit card. He's not depositing. He's getting a credit card. And they say the APR is 21%. What is the APY? Now, credit cards, all credit cards accrue monthly. So Bob gets a credit card that accrues interest monthly. That credit card has an APR of 21%. So if your credit card only accrued interest once per year, if you borrowed $100, that means you'd have to pay an extra 21 bucks, 21% of 100. But because they make you pay monthly, if you just kept paying off, or if you didn't make any payments, excuse me, which is not how credit cards work, we'll get into that much later. But if you didn't make any payments, you're going to end up paying more than 21% because of that compound interest. So our APY will be parentheses 1 plus 0.21, that's our 21%, divided by 12, raised to the 12 minus 1. So parentheses 1 plus 0.21 divided by 12, close it, raise it to the 12th, then subtract a 1. And we get 0.231 blah, 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 which when you can move it twice, multiply by 100, whatever, you get 23.1439, round to 2 decimal places, you get 23.14%. So when you're talking about smaller APRs, like 12%, it turns into 12.68 effectively by compounding monthly. So we gain an extra 0.68%. Now, if we're depositing money, that's cool. Let's say this wasn't a credit card. Let's say this was another depositing problem. If you found a way to get a 21% account that compounded monthly, that effective annual rate is actually 23%. You get an extra 2.14%. That's significant. Now, again, you're going to have a very hard time finding someone that is going to loan, that is going to take your money and give you 21% interest. It can be done in the stock market, but nothing's a guarantee, as we've discussed. Those things vary wildly from year to year, from day to day. They go up and down. There is no just flat annual rate of the stock market. It doesn't exist. The stock market is the moodiest thing out there. So just in this section alone, I've given you 4 formulas. I have given you on our formula sheet these first 4 formulas so far. You have got to understand which one you use for when, and we're not even done. There's another 4 formulas I'm going to be giving you that are even beefier. And they start using PMT instead of P. We'll make the distinguishing factor between that later. But for now, how do you know which of these 4 to use? Well, APY is the odd man or woman out because we don't give you an initial value generally, and they specifically ask for the APY, the effective rate. So that really is its own problem and shouldn't be too difficult to distinguish. But between these 3, how do you know when to use one of these first 2, which really you don't even need this one. I don't need to give you this formula. All I need to give you is this one. If we compound it annually, the ends would just be 1s here, which means they aren't needed in the same way they weren't needed here. That's why I've mentioned over and over that I really don't need to give you this formula. And I used to not give it to students. And I still believe you should memorize it. So how do you know whether to use the first one or the second one? It's all about whether we compound annually or if we compound more than once per year. How do we know whether to use the third one or the second one? It's about what we know. For this one, we know the starting value, which is P. Here, we know the ending value, which we call A. Now again, yes, this one also applies to that as well. These top two are really the same case. It's just whether we're compounding once or multiple times. And again, I could have given you a 5th formula here for this to be once, but at that point, we just don't. So you got to know which one to use based on what you have and what you're asked. You might be thinking, well, Mr. Beckner, why would I ever do a problem where I have the ending amount and I want to know the starting amount? All right, well, 30 years from now, after you left your money sitting in an account that earned 3% interest over and over and over and over and over, and your bank has changed names 3 times and they no longer have your records, maybe you're curious what you started with. You know you've got $57,911.12. What in the world did I start with? There's a context of a problem where you would know the ending amount and be curious what the starting amount is. Boom. All right. I don't want to leave any of this. I wish I could just hold that undo button. There we go. Now we can finally say 6.1 is done. And that means it can still be due on the 30th. I said we will not finish 6.2 today, so let's take that due date off, but everything else is perfectly fine. Go. 6.2, exponential functions. Well, wait a minute, Mr. Beckner, you've already been dealing with exponential functions. Everything you've said in 6.1 has been an exponential function, this constant percent growth. And yes, we have been. Everything from 6.1 was an exponential function. That is a fact of life. So why does the textbook call these exponential functions? I don't know. Sometimes textbooks just name things not too specifically, unfortunately. So I would actually just attach a couple words with more with. If I was the person labeling this, it would be more with exponential functions. And unfortunately, this is just the formula sheets that we went over so far. I just have them down there. I forgot that, in fact. That's where I was going to copy paste them from, but it's fine. It's fine. We're going to introduce something I don't want to introduce, and that is the continuous growth model. Continuous growth model, this is another exponential equation, but it really doesn't look anything like the last ones. This A is the P that we would have called that P before. So now we're just calling A the starting amount, and that's because that's the way the textbook does it. That's the way Excel does it, and it's Excel that we're doing this at all. Excel is the reason we're doing this at all. If we did a quantitative reasoning course without Excel, I would not teach this. But because we are naturally doing quantitative reasoning with Excel because they go hand in hand, I have to introduce this, and here's the reasoning why. This right here, this A times e to the kx, first of all, what's the e? You didn't tell me what e is. E is a number. It's about 3. It's 2.71828. I'll write that in a minute. But this thing right here, actually I'll scroll on to the formula sheet, is the same thing as this right here. So again, this thing right here, this y equals a times e, whatever that is, to the kx, is literally the exact same thing as this right here. It's just you let the in turn into, that's what this little arrow means, infinity. That's a terrible looking infinity. So instead of compounding annually, instead of compounding quarterly, instead of compounding monthly, instead of compounding daily, instead of compounding every hour, instead of compounding every minute, instead of compounding every second, instead of compounding every snap of a finger. In that little snap of a finger, when I compound continuously, I have just compounded interest billions and trillions and quintillions of times. Boom, there's quintillions of interest. Boom, there's quintillions of interests compounding. Boom, there's quintillions of interest compounding. So in calculus, you learn that this thing, when you turn that into the largest number in the world, infinity, it turns into this thing somehow. We're not going to worry about how. We just get the formula, and it's on your formula sheet. But I do this as A equals P times E raised to the RT. So I just use some different letters. And actually, I don't think I put that on your formula sheet now that I say that. No, I don't, because you won't have anything on the exam about it. That's why. Oh, if there's nothing on the exam about this, then why are we doing this? Well, there is still something. I won't have you plugging numbers into this formula, but you do have to go back and forth between them, and that's what we'll get to here. But let's start identifying what these things are. A is the starting amount, which I called P previously for principal. K is the, now this is very specific, continuous growth rate. R, as a reminder, R previously we called the annual growth rate, the annual percent rate. So in this model, this R really should be a K if you want to use those letters the same way. But it's just that if I were going to have you plug and chug numbers in, the value of R I give you would be the K, but that's not going to be the case for us. So don't let that confuse you. E to the K is a growth factor. So this E is a number, it's about 2.71828. It's actually pretty close to pi. It's very similar to pi in that it is an irrational number. It goes on forever and ever with no pattern. 2.71828, blah, 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 blah. If you pull out this calculator, if I hit second and then my division symbol, there it is. Now you might say 1828, 1828, you think that's a pattern. It's actually not. This 8 right here is a 7.9 something or a 7.7 something, so it's rounded. So it does actually go on forever and ever and ever without a pattern. So again, it's like pi in that it's actually pretty close to the same number. They're both about 3, but they have no pattern to them. So it's just a magical number that you don't need to memorize. It's in your calculators. So note, this is all we're doing in this course. We're not going to be plugging numbers into this formula and finding future values. We're only comparing to continuous models in this course because of how Excel chooses to display exponential equations. We much prefer the model like we had before. So I wrote the model as this, but you could have written it with these letterings, where the lowercase a is the P, the X is the T, the Y is the capital A. Or you could use it this way, where you have a Q and a Q sub 0. So Q is the ending amount, Q sub 0 is the starting amount. It's just different textbooks, different problems, different teachers use different notations. So I'm just giving you different ways that you might see it written at some point. So don't think just because I changed the letters that these are completely different. All 3 of those are all the same. It's just one teacher in textbook wrote it this way, one teacher in textbook wrote it this way, and one teacher in textbook wrote it this way. But contextually, we see a base amount times a growth factor raised to an amount of time. Base amount, growth factor, time. Base amount, starting amount, growth factor, time. So they're all the same things, just different letters. So in the formula sheet, I give you this version right here. I give you this version of the formula sheet, but in your homework, it may write it that way. Or in a group activity, it might write it this way. You have to understand they all mean the same thing. All right, so now what are we on? This is the only thing you'll be doing from this idea. Converting from a continuous growth rate, K, to annual growth, R, also known as APR. So some problems will give you the K and they ask you to find the R. Well, I said that this thing, this little blue circle right here, is literally the same thing as this right here. So these 2 highlighted things are the same. This and this are literally the same, just from a different angle. Instead of using a compounding every snap of a finger 10 billion times, 10 trillion times, to compounding just once per year. So remember in the last section what we were just doing, we were going between APR and APY. Same idea here. We're going between APR and APY. It's just a different formula. This is just another formula to go between an APR and an APY. It's just instead of compounding a certain number of times per year, we're compounding infinitely many times in a year. So this, this right here is the formula to go from an APR to an APY. So I'm not giving this to you on a formula sheet. This is something you have to remember. You have to remember that e to the k is the growth factor in one version. Then the 1 plus r is the growth factor from the other version. So you just set the two things equal to each other. So again, you must memorize this idea. It is not on your formula sheet. It is just setting one growth factor equal to another growth factor. This left side is the growth factor continuously. This right side is the growth factor annually. And we have seen that 1 plus r over and over and over and over and over. All right. Hold on, give me 15 seconds. All right. So we're going to pull up the guided activities from 6.2, and all this stuff says exactly what I was just talking about. Here we go. Guided activity 1, continuous versus annual rates. Again, the only reason we're doing any of this is because in Excel, remember how we showed you how to display the linear equations? Well, under those options, there was an exponential equation as well, and I even did a couple in class. You would get the dots between them, and you can see clearly that that is a much better model than a straight line. I know that's not that straight, but just bear with me. So this is the exponential model, and this looks nothing like any of the formulas we were working with in 6.1. Excel is not capable of displaying things in the formulas that we prefer. The p parentheses 1 plus r raised to the t. Excel can't do it. Excel only thinks in terms of compounding continuously. It's probably their one weakness. It's one weakness. So it displays things in this. So what the exponent here is will always be the k. That's the continuous growth rate. But we don't really like thinking as a continuous growth rate. We like thinking as an annual rate. That way we can plug that number into the formulas we had before. Because this amount of money in a fund, no one in the real world is using this model to calculate the amount of money in it. They're doing p times 1 plus r over n raised to the nt. Excel is just the odd man or odd woman out. So we're much more interested in going from one to the other. So that's what we're going to do here. We are going to convert k, the continuous rate, to an r, which is an APR, the annual rate. And how do we do that? It's right over here on the left. You set the growth factor of one version, which I've set as e to the k, equal to the growth factor of the other version, which is 1 plus r. So e to the k is e to the 0.1655. Set that equal to 1 plus r. Well, what's r? How do I get the r out of this? You don't. That's the unknown. That's what we're converting to. We're taking this, now that k, if it says 0.1655, that means it's 16.55%. But this e with that exponent number, that's the actual growth factor, and just to convert it to an annual, all we do is set it equal to 1 plus r. How do we do that? We subtract 1 on both sides. And then you just stuff all that in a calculator. Move this so you can actually see. So e, I got to go second, e with the exponent, which is right here on my calculator. And that exponent was a 0.1655. I can close it. I could have also hit second, the e that's under the division key, and then made the exponent myself. Then I got to do minus 1. And that gives us 0.1799. So that 0.1799829 is equal to r. But we got to convert that to a percent, so the decimal goes right twice. That's 17.99829. Now this k was rounded to 2 decimal places, so let's round this to 2, which would make it 17. The 8 would tell us to round up, so actually it becomes 18%. So a 16.55% rate that compounds continuously So if you had some money that you gained interest 10 quintillion times every time I'm snapping my fingers, you would need that account to have a 16.55% rate in order to match an account that gained interest once per year, earning 18%. That's the association here. So again, that's the effective annual yield. So 16.55% compounding continuously has an effective annual yield of 18%. So if you just gain money once every year, you need 18%. If you gain money, again, 10 quintillion times every snap of a finger, you need that effective rate to be 16.55%. That's the conceptual difference there. Now, this example, we went from K, we started with the continuous rate, and we found the annual rate. We can't go backwards. I cannot give you the annual rate and have you find the continuous rate, and that is because it uses some math that we're not going to do. And again, yes, the 18% here, we call it the R, which is the APR, but it is also the APY. You can establish that as either. But again, in the real world, when you go to get a credit card, you go to do a mortgage or anything, you're never going to see this number. Again, this K thing is only because of Excel. This is not a real world issue. However, if you're modeling something, your finances, and you're making spreadsheets and graphs, if you wanted to see the equation, it's going to spit out the K. You would be more interested in knowing the R, so that this is what you would do. All right. So let me clear my screen. Let me scroll and see if there's anything else I need to do in 6.2. I think that's it. 6.2 is a really short section because 6.1 is so long. Let's do one more of those and then we'll call it a day. I might take an extra minute of your time. All right, US population. So here, this one. Now the number in front is the starting population. This is the starting amount. Can you see why it really doesn't make sense a lot of times to use this type of model? We started with 0.0036 of a person. What? That's just weird, but we don't need it for this problem, so just ignore it. What we really need is the K, which is the exponent number. Now, if it's negative, that would mean that we're going to be decreasing over time. We would be losing. And while I'm not going to have time to do example 3, please look at it on your own time on page 232. Please look at example 3. You'll see a negative K. You'll see that this thing is going down instead of up. And that's called exponential decay. All right, so the K is 0.0126. So we're just setting that growth factor equal to 1 plus R. So we go e to the 0.0126 equals 1 plus R. We subtract 1 on both sides. And then we use our calculator to get that number. Second, e with the exponent, 0.0126, close it, then a minus 1. So that will be the answer as a decimal. So R is 0.01267797. Let's move that decimal right twice, so it's right twice, so 1.26797. And that's our percent, but we want to round this to 2 decimal places, which is 1.28%. That's our effective rate, which we're also calling an APR here. So the APR is the EAY is the APY when you're comparing continuous to annual. Now the K as a percentage was 1.26%. The R was 1.28. These are so close to each other. You know why they're close? Because we started out with a much smaller value. Remember I said earlier, effective rates are much closer to the actual rates when you're dealing with like 1 and 2%. When you start dealing with 20 and 30%, they start having more space apart. Like the last example we did with number 1, where the K was 16.55%, but the R was 18%. So the larger the rate, the further those two things are apart from each other. Now again, nobody in the real world is going to be talking about population growth as a continuous model where it started with less than 1 person. It just doesn't make sense as a model itself. But Excel, that's just the only way it can think. So it kind of it kind of manipulates the numbers into a different model that's more advanced than what we need. So again, this idea is not something we're going to see in chapter 8 or 9 again, but the idea of converting from one rate to another, we will see, because if you do modeling on your own in Excel, it's going to spit out numbers like this if it's exponential growth, and you're going to be wondering, well, what's the annual rate? So you need to do this. All right. I'll tell you what, that actually does close out 6.2. So I said 6.2 wasn't going to be due that day, but it is. I forgot how short the section is. And I had given you till December 1st, which is a week from today. So we do have a few things due on December 1st, so please use your time wisely. You know what, I'll even give you an extra day on that. We'll do December 2nd. I'll give you one extra day on that homework, just so we don't have 3 things due on the same day. I don't like that. And I'm sure you didn't either. All right, so if you have any questions, please email me. Besides that, take care. Well, there is no class Thursday. It's Thanksgiving, so enjoy your short break. Eat as much turkey or vegetables, whichever you prefer, as makes you happy. I hope you get to see your family in the midst of all this chaos. So please take care. Please study hard. Please work hard. We're near the finish line. Let's not slack at this point, all right? All right.